Okay, so here we are, number 6. We're going to talk about number systems. Now this should be a review, but we're just going to clarify, make sure we all are on the same page when it comes to number systems. So number systems are different ways of grouping numbers by common properties or qualities of those numbers. And these overlap. We're going to see a little lower. We have a nice Venn diagram there that will kind of show where these overlap and relate to each other. So our first set of numbers are the natural numbers, or n. And these are the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. We kind of also know these numbers as our counting numbers. So they're often referred to as our counting numbers. They're the first numbers that you learned when you were way back in a little child, yes. Now, when we add 0 to that equation, we then have our whole numbers. So our whole numbers are the counting numbers plus 0. So the only difference between counting numbers and whole numbers is that we incorporate in 0 into that configuration. And we've been using those for probably not much longer than we've been using counting numbers, because we're pretty familiar with whole numbers as well. Then when you hit your junior high years, we started talking about integers. Now it's important to note, ladies and gentlemen, folks, that integers are notated by an I, whole numbers by a W, natural numbers by a capital, and they're all capitals. Okay? Now the only difference between integers and whole numbers and natural numbers, sorry, wrong pen. This is Finley, come on, is that there was our counting numbers. Then we added a 0 for our whole numbers. And then with integers, we start talking about the negative numbers, right? So here we have positive and negative numbers, okay? They're still whole numbers in that there's no part numbers included at this point, but we've included the negative, the opposite side of the number line. When we start to get to part numbers, then we start talking about rational numbers. And we would think, oh, wouldn't it be an R? But no, it is a Q because we have an R later on, okay? Now, rational numbers, basically, it's anything you can write that can be written as a fraction. Okay? These include fractions, obviously, because you can write those as a fraction. Right? Fractions, as well as terminating decimals. Terminating decimal means that they stop, right? So there's a finite number of decimals. And then it also includes repeating decimals, because you can write those as a fraction, because this 0.3 repeating is the same as 1/3, okay? So 7/9 gives you 0.7 repeating, 7. So it would, repeating decimals, there are patterns for how you can write those as fractions. However, there are some numbers that are irrational. Irrational numbers look like rational numbers. They're a Q, but it has a line over the top. So these include non-repeating, non-terminating decimals, okay? So, for example, you might have square roots of non-perfect squares, or pi is our most famous irrational number, root 2. So that has an infinite number of decimals. Okay, they go on forever. Okay, now the real numbers, and this is why we couldn't use an R for rationals, real numbers are includes everything, okay? So they're all included within the real numbers. So how does that look? So this whole big thing, dun, 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 is all of our real numbers, okay? Okay, now within the real numbers, we have subgroups. We have our rationals and our irrationals. They don't overlap, okay? And within our rationals, we have our integers. And then within our integers, we have our whole numbers. And then within our whole numbers, we have our natural, okay? So they're kind of nested in this beautiful Venn diagram, okay? And like I said, you may have seen this before, but it's just a quick refresher. So let's take a look at comparing some. So we're going to place a check mark in each family of numbers that each belongs to. So the number is minus 56. I'm going to actually do some X's as well as check marks just to kind of rule things out. It is not a natural number because it's negative. It is not a whole number because it's negative. But, it is an integer. It's also rational. If it's rational, it is not irrational. It cannot be, it has to be one or the other. And of course, all numbers are real numbers. Okay? In fact, we can go and we can put a check mark down every single place for real numbers. Because if it's a number, it's a real number. Okay? Now here we have 0.666 repeating. It's a decimal, so it is not a natural. It's not a whole number. And it is not an integer. However, we have to decide if it's irrational or rational. We would decide that it is rational because it's a repeating decimal, and we've included that as our rationals. Okay? 0. Not a natural, but 0 is a whole number. It is an integer. It is rational. It is, however, not irrational. Negative 0.4874 or 478, negative 7.47487 ... The ... means it goes forever. Well, we know it's not natural, and it's not whole, and it's not an integer. Okay? It's whether it's rational or irrational. This one would not be rational because it's a non-repeating decimal with no end in sight. Okay? Next one is our fraction, 7/2. It's a fraction, so it's not natural, not whole, not an integer. We can write it as a fraction, so it would be a rational number. Therefore, it is not irrational. It cannot be both rational and irrational. Okay? Negative 4.181818, and so on. So it is a repeating decimal. So it's not natural, it's not natural, it's not whole, it's not an integer, and because it repeats, we would say it's an irrational, okay? Or it's rational, sorry, so it's not an irrational. Repeating decimals are rational, okay? We have a terminating decimal here. It's not natural, not whole, not an integer. It's a terminating decimal, so it's rational. So we can rule out irrational. Square root of 25. Well, the square root of 25 is equal to 5, right? So let's see, where does it fit? Well, 5 is a natural number. It's also a whole number. It's also an integer, and it's also rational. It is, however, not irrational, okay? For these ones, you need to evaluate to tell. When we take the square root of 7, we get 2.645 ... non-repeating decimal. So it's a decimal, so it's not natural, not whole, not an integer. Is it irrational or rational? Well, it's a non-repeating, non-terminating decimal, so it would be irrational. Oops, wrong color pen. So it would not be rational. It would, however, be irrational. Okay, so there's some sorting out. Use the Venn diagram to help you if you're not sure, to just kind of tell where do things fit. When using the calculator, if the index is any other number other than 2, then one must use the following steps. So this is when we're finding roots, okay? So for number 4, okay, this is it's going to depend on your calculator. So you probably have that X root Y button, and it really depends on your calculator. You all have different calculators, so we can walk through that in person. You can ask me personally, or we can check it out online. So determine whether each number below is rational or irrational. Use your calculator. So if I go cubed root of 9, so 9, second function, cube root, I got, so for here I get 2.08008, blah, 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 blah. It's a non-repeating, non-terminating decimal, so it would be irrational. Okay. Square root of 14, so 14 square root, I get 3.7416 ... Again, non-repeating, non-terminating decimal, it's irrational. Square root of 2 over 9 is the same as, 4 over 9 is the same as 2/3. So this would be rational. Okay. Cube root of minus 125. So minus 125, second function. Five times 5 times 5 is 125. So the cubed root, this would be -5. So it would indeed be rational. Okay. It's also an integer, but it's just asking rational or irrational. Okay. Square root of 1.32, I get 1.1489 ... Sometimes you'll get a terminating decimal with these, so it would be rational, but these are not. This is a irrational. And then the fifth root of 32. Well, 32 is 2 times 2 times 2 times 2 times 2, 2 to the 5th, right? So this equals 2. So this would be rational. So be careful with these. I'm looking at the other teacher's notes and they had an error, so I'd rather you not follow that. Boo-boo. Okay. Radical form to exponential form and vice versa. So we're still continuing with radical forms. Okay. I might go into this in more depth in another unit, but we're going to talk about it right now. So radical form versus exponential form. We can write the square root as 7 to the 1/2. So basically, the rule is the nth root of x is equal to 1 over x to the n. So if I'm finding here the square root of x, it's like, square root of 7, it's like 7 to the 1/2. Similarly, if I'm finding the cubed root of 2, it's like 2 to the 1/3. The index becomes the denominator of the fractional exponent. Okay, we're going to do some examples and some practice to kind of see how this works a little more. But this will help us manipulate things later on. So express each of the following exponents in radical form and then evaluate. So sometimes you're going to get a fraction for your exponent, but we can change these to radical form. So 64 to the 1/2 would be the same as square root of 64. Square root of 64 is, well, 64 is 8 times 8, so the solution would be 8, okay? The 32 to the 1/5 is like the 5th root of 32. Well, remember, 32, 5th root of 32, it's 2 times 2 times 2 times 2 times 2, 5 times, so the answer would be 2. Cubed root of negative 216. Okay, I take the 3, the bottom of the fraction, I put it in there. Now, 216, if I find the cubed root of it, I can do a factor tree, I can use my calculator, and I'll find out that it's negative 6 times negative 6 times negative 6. So this would be negative 6. Okay, and here it's going to be the 4th root of 16. Well, 16 is 2 times 2 times 2 times 2, so the answer would be 2. Okay, remember, when it's a cubed root, you're looking for triplets. When it's a 4th root, you're looking for groups of 4. When it's a 5th root, you're looking for groups of 5. Okay, it's the same rules that we did for squaring and cubing. We now just have more numbers. Okay, radical form here. So this would be the 4th root of 16 over 81. Well, 4th root of 16 over 81, so we're looking at, I'm going to write it down here. 16 is 2 times 2 times 2 times 2, and 81 is 3 times 3 times 3 times 3. So we're circling groups of 4, so we would get 2 over 3. Okay, here this one's a little easier because it's just a square root of 4 over 9. Square root of 4 is 2. Square root of 9 is 3. Okay, here we would have square root of 100. The square root of 100 is 10. And then finally we have the cubed root of negative 8. Remember, cubed root, we've got a negative sign, so our answer is going to be negative. So this will be negative 2. Okay, it's a cubed root, so looking for 3 of them. Okay, all right, that kind of got thrown in there at the end in terms of the radicals to exponents. I might take some time later on in the year to do a little more practice with that because that's actually a pretty important concept. And the better you can get that now, the better it's going to help you in 10C and then later in 20-1 or 20-2, whichever one you go to. But I think that's enough to kind of give you a dip your toes in the water kind of.